So last time we got into obviously chapter 2 there, we were talking about measurements. We talked about how to obviously properly take a measurement. Remember that when you do take a measurement, there's always some degree of uncertainty, as we talked about. The degree of uncertainty really depends on the piece of equipment that you're using. So there's really always two things you want to look at when you're taking a measurement, for example, with some type of glassware, or even maybe with a ruler. The first thing you want to look at is what does the biggest markings represent? So usually on most scales, there's big markings and there's small markings. So you want to figure out sort of what does the big markings represent. The next thing that you want to figure out is how many of the little markings are there between the two, and how much each little marking represents. And as we talked about and as we saw, for the most part, you're able to take the reading to one more place to the right of the smallest marking. So I think we had one where the smallest marking represented, for example, 0.1 centimeters. We were able to take that reading one more place to the right and take it to really 2 decimal places. So in general, again, not 100% of the time, that is the case, but pretty darn close, 99% of the time it is. You can figure out what the smallest marking is, and you should take the reading to one more place to the right. When we do take a measurement, as we talked about, it is typical to record all the certain numbers. And again, those are numbers that no matter who takes a look at the measuring device, everybody really should agree upon, it is at least that much. And then we should always record the first uncertain digit. And that first uncertain digit is really where the error is. Again, I may look at something as we saw in a couple of examples and go, I think it's like halfway there. Other people may say, I think it's further than half or less than half. And that's really where that estimate comes into play. For the most part, it's plus or minus 1 of sort of the estimated digit or that uncertain digit. When we take all those together and we take a measurement like that, that does represent what is referred to as significant figures. So within a measurement, when you record all those certain numbers plus the first uncertain number, you basically can figure out how many significant figures there are. We also talk about really important that even if it happens to look like it's like dead on a line, and you have the ability, for example, to go to the second decimal place, you do need to put something like a 0 there for the second decimal place to maintain sort of the proper measurement that you made. As we talked about, if you lop off some numbers in your measurements, you're really making your measurements a lot crappier and a lot worse. For example, there is a big difference if we report a measurement as 2.4 versus 2.40. 2.4 means, again, it could be as high as 2.5 or 2.3. There's a pretty big gap there. 2.40 means it could be like 2.41 or 2.39, much better measurement and stuff like that. So again, remember that if you do have the ability to do so, you should always keep the correct number of significant figures by putting a 0 there. Again, in cases where you feel it's like right on a line or something like that, perfect there. Obviously, digital numbers, or if you use anything that is digital, that's also a very common mistake that people make. Again, if it is digital, then pretty much all the numbers are important. So you should always record everything that's important. Probably in your case is the balance or the scale is probably where you will see something that is digital, and it's very common. Also, people will just like leave off numbers and stuff like that. So if it's digital, it displays you a number. Probably they're all significant, and you should record it. Any questions on that? So. Then we got into sort of the rules for counting significant figures. And there's really sort of a couple of type of rules. First off, obviously, anything that is a non-zero number is significant. And that's really where you start counting. So you go left to right on the number, you hit the very first non-zero, and that's when you should start counting as to how many significant figures you have. And then there's basically zeros, and there's 3 types of zeros that we talked about. There's a bunch of zeros that come before you hit the first non-zero number. Those are leading zeros. Those are not significant. So you can have like a million zeros until you hit the very first non-zero. They would all be not significant. We then have zeros that really do come between 2 non-zero numbers. those guys are going to be significant. And the zeros at the end is really the one that gives, like I said last time, everybody sort of a difficult time. The zeros at the end will be significant if there is a decimal point in the number. So I think we looked at a couple of different examples. The zeros and the decimal points at the end do not need to be near each other. You just need to simply have a decimal point in the number to make every single zero at the end that's significant. For example, I think we're looking at this here. 600 with no decimal point written. Again, these zeros are technically not significant, which means in that case, that guy did have only one significant figure. By just putting the decimal point there, it now makes those zeros, even though they technically come before the decimal point, but they do come at the end of the number in terms of there's nothing else after those zeros. So they're still trailing zeros and they would become significant, and it is 3 significant figures. And I think we did that guy up there on top. But again, if you had something like this, this would be where we would start counting at that one. These zeros would be trapped, so they're significant. That obviously is significant. Then all 3 of these zeros, again, even though they are way far away from the decimal point, is going to be significant because of the decimal point that is there, which means in this case, 1, 2, 3, 4, 5, 6, 7 significant figures that guy would have. Any questions on how to count significant? I think the last thing we also sort of talked upon or touched upon here is, sometimes you are asked, to identify what digit is the estimated digit or the uncertain digit. And remember, it really is the very last significant figure. And again, may not always be the very last number that's written. So again, the 600 here is a prime example. The estimated digit is actually the first guy, is not the last digit that's written, as opposed to the 600 on the bottom. It is actually the last digit that's written. I would say in most cases, it probably will be a lot of times the last digit that's written, but it's not technically the last digit, but it is technically the last significant figure that you have in that particular number. Any questions on any of those? All right. And we'll continue on. So here, just looking at some of these, obviously we would again start counting here at the 3. That is a non-zero. Everybody else after that is non-zero, so they would all be significant. Here are 5.6, same deal. All non-zeros would be 2. This guy again 3, and this guy in this case would be 5. Again, you always want to start left to right on the number, and you want to start counting as soon as you hit that very first non-zero number when you do it. Here are our zeros examples. Again, starting here, we would start counting up to 5. Zeros are trapped, which makes them significant. So all 4 of those guys are significant. Here, the 2 is where we start counting. The 0 in the middle, trapped, so it's significant. So all 3 of them would be significant. Here again, we do not start counting until we hit the 7 in this case, as everybody before that are zeros, and they're referred to as leading zeros, which are not significant. So starting at the 7 is significant. Obviously, the 0 now is trapped between 2 numbers, which makes it significant. And the 2 is obviously significant as well, which gives you 3. Same thing here. We would not start counting until we hit the 4. And then obviously the 0, 5 are significant, and the 0, 5 is significant, which gives us 5 significant figures. Questions on any of that? And again, our zeros at the end, you see here 200 minutes written like that, no decimal point written. It is one significant figure. Starting counting here on this guy, which is a 4. All 3 of these zeros are significant because of that decimal point that we see there. And that would give us 4 significant figures in this case. Thank you very much. Now, if we were talking about which one is the estimated digit in the 200, which one would it be? Which is it? It is the 2, yeah. So again, this has one significant figure, which means really that first 2 is our estimated digit. Again, here you do not see it's the last number, and this was 40, right? The estimated digit here would be, it would be the last zero in this case. So again, in a lot of cases, the estimated digit is that last number, but not in 100% of cases. And this is really the place where, you know, it is. Any questions on this? And here's a few more. Again, starting to count at the 4. That's significant. The 4 and the 0 at the end, again, going to be significant because the decimal point gives us 3. We do not start counting on the next one until we hit that 2. That 2 and the 2 obviously is significant, which gives us 2 significant figures. And clearly all these zeros are leading zeros. Sometimes people are confused, like, what about, like, you know, these zeros, they come at the end, but they are not technically at the end. The end would be after the last non-zero number. So these are all considered leading zeros in that case, which means they are not significant, leaving just the 3 here as our significant figure. And also in this case, it would also be our estimated digit, as there's only one significant figure. And again, 44,000 would be 2. Again, no decimal point written. In the case of counting sort of significant figures, I know sometimes we assume like, hey, there's a decimal point at the end of the number or something like that. In the case of this, they would write it if they meant to write it. So if you do not see it, then you can assume it's not important. And again, it would be our estimated digit there. The 8 and the 1 being significant here, with the 1 being the estimated digit. And obviously the 615 here is significant, again, with actually the 5 in this case being the estimated digit. We do need all these zeros. You might be wondering, so why do we need all the zeros? Because obviously if we crossed out the zeros, 615 is very different than where I crossed out there 6 million or whatever that is there. So there's a very big difference. So they're kind of like placeholders, will, to maintain the value of it, but they're not really significant figures. So we can't get rid of them. As we talked about last time, we never want to get rid of, you know, extra digits and stuff like that. This also, as we talked about scientific notation, right, is whenever you write that number in scientific notation, all the numbers that come before the times 10 part are always significant. And that means obviously in this case, in terms of counting significant figures, we would just look there and we see all 3 of them would be significant. Here we see 2. And obviously here we see 2, 4, and 5. Because it typically needs to be a number between 1 and 10 in scientific notation, you typically will always find yourself with a decimal in that number. And that means any zeros that come at the end will still be significant for the same rules. Also, I think we might have talked about, but just a reminder, you know, if you had something like 125,000 written like that, that has how many significant figures?
3.
That's 3 significant figures. And it would be these guys. If we were to turn this into scientific notation, 1, 2, 3, 4, 5 places, we would want to write it like this, because now it still has 3 significant figures. We actually would not want to carry over all those zeros, because now it would have how many significant figures? All those would then technically be significant. 1, 2, 3, 4, 5, 6 significant figures, where our original number only had 3. We somehow gain extra significant figures, which shouldn't happen. So when you go from sort of decimal form to scientific notation, or scientific notation back to decimal form, you want to always maintain the same number of significant figures as you do so. We're going to talk about doing some calculations here with significant figures in just a second. And again, sometimes the only way to sort of present the answer in the right number of significant figures is to write it in scientific notation. You know, so for example, if I did have an answer that was like 13,000 and I wanted to display it as, you know, 3 significant figures, there's no way in sort of decimal form that I could do anything to that to get it to 3 significant figures. If I put a decimal at the end, it would have 5 significant figures, right? if I put a decimal, you know, like here, it still have 5 and stuff like that. So, you know, really the only way if I wanted to present my answer in scientific are 2 3 significant figures, I would have to write it in scientific notation, keeping just one of the zeros there. And that would give me 3 significant figures and it would still be 13,000. So, you know, if you find yourself in a calculation, you're like, hey, I gotta get this number into like 2 significant figures or 3 significant figures, and I can't figure out how to do it sort of decimal form. You may have to give the answer in scientific notation because you could kind of control how many significant figures you put into that number. Questions on that? All right, so again, this is just displaying what we just talked about, 3 significant figures. When we translated 3, this has 1 significant figure, which is again why all the zeros basically disappear. This has 2 significant figures, so we maintain it. So again, as you go back and forth, you want to make sure that you do maintain the right number of significant figures. You don't want to give anybody more or less significant figures when you're going from scientific notation decimal or backwards decimal to scientific notation. All right, so take a second here, identify the significant and non-significant zeros in each of the following and write in scientific notation. We'll just go with how many significant figures in each and write each of them in scientific notation correctly. Okay, let's take a look. So starting with the first one, again, we would start counting there at the 2. The 2 is significant, the 6 is significant, the 5 is significant. Is the 0 at the end significant? Yes. It is because there is a decimal point there. So this guy would have 4 significant figures. We then need to turn it into a number between 1 and 10, which means we need to take that decimal and go 1 place, 2 places, 3 places to the right. Because it has 4 significant figures, we need to keep everybody there. And we're going to say there 1, 2, 3. And it would be a -3 as it's a small number. Again, we do need to keep the 0 in this case. If we just wrote 2.65, that would be 3 significant figures. We just wrote 2.6, it would be 2. So we do need the 2.650. Any questions on that one? Looking at this one here, starting at the 4 is where we should count, and pretty much the only 0 that we see there is trapped between 2 non-zeros, which makes it significant. So that's a 2, 4, 5 significant figures on this guy. In this case, the decimal point just needs to go 1 more place to the left, and we would need to again keep every number there, giving us still the 5 significant figures when we turn it into scientific notation. Again, if you get rid of any of the numbers, you just shorted the number of significant figures. Lastly, here, a lot of spaces between numbers. This guy has how many significant figures? See? 4. It is 4. I don't see a decimal point anywhere. Those that I underline are significant. The 3 zeros at the end would be non-significant or not significant because there's no decimal point. That means we would assume, for the sake of scientific notation, that the decimal point would start here. So we would go 1, 2, 3, 4, 5, and 6 places there to the left. And that would yield us 1.044 times 10 to the 6. Again, in this case, we would drop the zeros to maintain the significant figures. Any questions on that? And obviously, we talked extremely important last week about when we do punch these into our calculator, right? We want to make sure we use our exponent button. If we are punching something in scientific notation into our calculator, I want to make sure you always use those 3 buttons or one of the 3 buttons that we talked about. You know, one of those 3 buttons there when you do put a number in scientific notation. Any questions on that? As we also talked about, you do not need to write every answer in scientific notation. You can if you want, but you don't need to do so unless the instructions say to do so. But again, as we talked about, sometimes the only way to do sort of the right sig figs is that scientific notation. So you might have to do that. Exact numbers, I think we also might have talked about, but exact numbers really are, you know, they're just things that we typically would count. Are these type of definitions or equalities? And really the deal with exact numbers are, if you come across an exact number, essentially it could have as many significant figures as you want, because it's an exact number. Really where we sort of come across exact numbers sometimes, or a lot of times, is in calculations or conversions. And in the case of that, we don't have to worry about significant figures that involve those guys, because they technically have as many as you want. And again, these are all considered exact numbers, things that we obviously, if we had donuts, baseballs, or capsule, we would just count those. These are metric to metric conversions, which are definitely considered exact numbers. US or English to English conversions are also considered exact numbers. There are some crossovers that are, like 1 inch is the 2.54 centimeters. That's considered an exact sort of number. But for the most part, if you cross over between those two things, a metric to US or English conversion, or backwards, whichever way. For the most part, those are not usually considered exact numbers, which means technically speaking, if you come across one of those in a calculation that you're doing, you do need to kind of look at the significant figures to figure out how many significant figures your answer should have. And we're going to talk about how to decide, how many it should have in a second, but you do need to consider those. For the most part, I'll say 99% of the time, but maybe like 95, 97% of the time, if you have something that's sort of an equality, like any of those that are on the board there, 1 foot equals 12 inches, or even if you cross over from metric to English, probably 95, 97% of the time, you could probably ignore it and still be right. But technically speaking, if you kind of cross over metric to English type conversion, you are supposed to sort of look at them and determine the significant figure. All right, so let's take a look at each of these and decide, are they measured, are exact, and give the number of significant figures. So if we have 3 coins, that would probably be exact, which means that we're going to have as many sig figs technically as we like. Diameter of a circle is 7.902 centimeters. That is measured, which means significant figure wise it has. It does have 4 significant figures. Again, all those being significant. 60 minutes is 1 hour. It is an exact. Again, it could have really as many sig figures as you want. Questions on any of that. All right, take a second and run through these number of sig figs in each of these.
We have how many sig figs? Should be 2. Again, the last 2 would be significant. Next one has 4. All of them would be significant, including that last one. Here we have 1, which would be the 8. And lastly, we have 3. Perfect. Again, the 0 at the end being significant because of the decimal point. All right, so going through this one, if we look at these 3 answers for letter A, we're looking for the one that has 3 significant figures. First off, the first one has 4, this one has 3, and this one has, perfect. So that would obviously be that one. For part B, this one does have 3, this one has 5, this one has 4. So obviously it would be that guy. And lastly, the number of significant figures in this number would be, it would be 3. All of those guys would be significant in that particular case. For B, yeah. Which one would be 2? Oh, would the answer be 2? Is that what you're asking? Oh, they changed questions. I should read the questions. The screen changed? Oh, that's that screen. How about we remind me later? How's that? What happened there? All right, let's see that. All right, sorry. Oh, you're right. I probably should read the question. That usually is helpful, right? So, so that would be 3 significant figures was the first question. Clearly not this question. So let's read that question. We're looking for all the zeros are significant And in this case, the ones where all the zeros are significant is everyone but the one I circled. Yeah, so we'll box them. These are all significant, right? All the zeros at the end are significant. And obviously the zeros here are significant as well because it's a scientific notation. So good point. You should read the question. Bad, fail, all those things, right? So did I get the last one? I read the last one, so that's good. All right. Any questions on that? Thank you very much. Questions on that one? There? All right. It's always, who's got time to read questions, right? All right. All right. Now that we've identified how to count significant figures and all that good stuff, let's talk about really when we do calculations, is really the important part is how to properly give your answer to the correct number of significant figures. You always want to do that. And really when we do calculations, there's really kind of two sets of calculations we do. We typically will either multiply. One of those days, multiply or divide. Let's go back to sleep. All right, multiply or divide really badly there. When we multiply or divide, what we look at is our answer should have the same number of significant figures as the number with the least number of sig figs. So if you find yourself in a calculation where you're multiplying or dividing, what you want to do is your answer should end up with the same significant figures as the one with the least. So if we were to take 3.25 and multiply it by 1.2, and as we talked about before, our calculator does not always give obviously the answer to the proper number of significant figures. In this case, we will end up with 3.9, which it actually did in this case. We would look at this guy, which has 3 significant figures. This guy has 2 significant figures. That means that our answer should end up with 2 significant figures. So if you multiply or you divide, what you're looking at is the number of significant figures, and it's always the smallest. So the smallest one is kind of, you want to think about it, the smallest one is your worst measurement. So it's the one that really limits how good your overall number is. So it's the smallest number of significant figures is what your answer should end up with. So multiplying or dividing, sig figs for the answer should equal the sig figs for the smallest number. The other thing that we do is adding or subtracting. Now, when we add and subtract, what we're looking at is the answer should end up with the same number of decimal places as the number with the least number of decimal places. So multiplying, dividing, we actually look at significant figures. When we add and subtract, we're actually looking at decimal places. It is the least. So if we had like 1.200 plus 3.4 plus 1.0000, if we added all this stuff together, we would have 0, 0, 0, 6, 3, 4, 5. Where should I round this number to? So when we're adding here, we're going to look at decimal places. This one has 3 decimal places. This one has 1, and this one has 4. The smallest is 1, which means we should lay it up right there at 5.6. So adding and subtracting, again, smallest, but you're looking at decimal places. When you multiply and divide, you're looking at significant figures, also the smallest. Also to remember that 5.6 does have one decimal place, but how many significant figures does this have? It does have 2 significant figures, which may be very important if you're continuing on and doing another calculation with that number. So that's very, very important. Question on that there. Now, what happens if we do sort of multiple steps, which sometimes happens? So, you know, let's say we were going to take 3.2 times 1, 2, 3, 4, and we're going to divide it by 5.66328. Now, if we were going to do all this math, which part would we do first? We typically would do the part that's in the parentheses first, and there we're multiplying, right? So forget about what the answer is, but we're multiplying. We're looking at significant figures, which means technically speaking, this first number has 2 significant figures. This next number has 4 significant figures. That means technically speaking, when you get the answer for the top, it should have how many significant figures? It should have 2 significant figures, that answer at the top. The next thing you would then do is take that number and divide it by this number on the bottom, which you would still be looking at significant figures. So you'd be taking 2 significant figures on top, divided by 6 significant figures on the bottom. That means when you're all said and done, your answer should end up with 2 significant figures. So sometimes you do multiple calculations in a row. You need to kind of keep track of the sig figs and all that. And really the best idea on that is try not to round to the very end. And then you really should clean it up to the right number of significant figures. If you sort of round along the way, a little bit here and then a little bit there, by the time you get to the final answer, you may find yourself very far away from the real answer. So it's good practice to sort of maybe not round so much if you're doing definitely multiple steps in a calculation until you get to the very end and then kind of clean it up at that point. Personally, when I do calculations, I just keep up the whole numbers and just keep going till the end and then sort of clean it up. You do want to kind of keep track and stuff like that as you're doing it. Any questions on that there? Now, rounding is really important as well. We want to round. Normal rules apply for rounding, right? Which is if it's like less than 5, we just kind of drop the numbers we don't need, right? If the next number to where you're going to round to is above 5, right? We round up, right? In that particular case. Remember, we don't want to ever do any sort of extreme rounding or anything like that in an effort to get the right number of significant figures. So again, if you know you had a number like 13,333 and we're looking for 2 significant figures, what would the answer be? 1.3. How about 13? How about 13,000? So let's take a look at each of these and see. We're looking for 2 significant figures. How many significant figures does this number have? Has 2. How about this one? And this number written like that has. So they all have 2 significant figures, which is good. But let's say we turn this into money and I owed you $13,333. And I say, I'm going to pay you 2 significant figures. Here's like $1.3. Not going to make it out of the room, right? There's a very big difference in the meaning of this number and the meaning of the number we're really looking at. Same thing with 13. Maybe you let me get out of the room with $13. I doubt it because there is, again, a very big difference between $13 and I owe you $13,333. $13,000 has 2 significant figures. It is, in terms of meaning, relatively pretty much the same thing. And maybe you just give me the $333 teacher discount and, you know, we're probably okay in that case. So it is a very common mistake that a lot of people make is they have focus on, I should give the answer to the right number of significant figures, which is good. But sometimes, you know, they do such extreme rounding that they kind of change the meaning of the number. So you never ever want to change the meaning of the number, you know, to get yourself to the right number of significant figures. We could, as was, I think maybe where the 1.3 came from, we could have, if we wanted to, also did a 1.3 times 10 to the 1, 2, 3, 4 and write it in scientific notation. And that also would be two significant figures. So, you know, you could have done scientific notation on this one and got yourself to two significant figures. Any questions on that there? All right, so always important when you do calculations, you should always try to end up with the right number of significant figures. Again, multiply, divide, they're both the least, so least sig figs, adding, subtracting, least number of decimal places. All right, there's our rules for rounding as we talked about. 4 or less, we drop. 5 or more, we round up. All right, so again, here, if we want to round to 3 significant figures, we would look at the 2, and then we would look at the number next to it, which is a 3, and we would drop the rest of it. If we wanted to go to 2, we would then drop the rest, and so forth, like we talked about here. We would look at the 7. The next number is an 8, which obviously is above 5. So we would round that to 14.8 for 3 significant figures, and 15 if we were just shooting for 2. And lastly here, if we were going for 3 sig figs, it would go here, and we would look at the 6. So we would round it up to 3260. Again, you do need that 0 there, right? Obviously, if you dropped it, you would have 326, which is obviously very different than 3,260. All right. All right, take a second and knock that out there. 3 sig figs and 2 sig figs. All right, so first off, the original number here has 4 significant figures. So we now want to take it to just 3 significant figures, which in that case would take us to the 4. We want to look at the 5 that's next to it, and then in that case, we should round up. Which means we should end up with 3.15. Do I put the 0 at the end? I do not, because then it would obviously have 4 significant figures and lay up the units there as grams. Now we want to take the same number to only 2 significant figures, which would take us to the 1. Looking at the number next to it, which is a 4, which is less than 5. That means we're just going to drop those numbers, and in this case, 3.1 grams. Yeah. Any questions on either of those? Right, just the following calculated answers to 3 significant figures. So looking at these numbers here, we would go that's significant, that's significant, that's significant. So that would be 3 significant figures. Here we want to look at the 7, which obviously is above 5. So that's going to look like an 825 centimeters on that. Looking at this one, again, we would not start counting until we hit that 1. And that means that the 2 there is the 3rd significant figure. And looking at the next number, which is a 4. So we would simply just drop all those guys and end up with something that looks like 0.112, which is 3 significant figures. Lastly here, this guy has how many significant figures to start with? It has 2, but we need 3. So I need to put we'll add a 0 in there. This 0 now is significant again because there is that decimal point that is in that number. Any questions on any of those there? All right, so as we talked about, remember, again, your calculator does not always give you the correct number of significant figures. This is sort of an example like we were just talking about a second ago. Technically speaking, we would do sort of the top part here. This guy has 2 significant figures. This one has 4 significant figures, which means technically speaking, when we get the answer, you know, we would have 2 significant figures for the top. Would I round that number? Truthfully, probably not. At that point, I would keep it in my calculator, probably continue on. The next thing we're then going to do is divide that number by the number that's on the bottom, which means we're still looking at significant figures, and that is 3 significant figures. So again, our answer should end up with 2 significant figures. That obviously is what you get when you punch it into your calculator. you need to obviously then trim it down to 2 significant figures at that point. Any questions on that there? Yeah. Yeah, I'll give you two. I'll give you two answers to that, but the main answer is no, probably. But you know, if you're doing maybe something that's just a straight significant figure like problem like this, like you know, what give the answers a proper number of sig figs, you could, but it's really not good practice to do so. I personally, like I said, I would multiply the top number and then divide by the bottom, kind of like what they did there, and you'll end up with that long number and get it. Sometimes if you feel like you need to write down a number, for example, for the top number, and you want to kind of write the number down and then use that number to do the calculation, truthfully, it's good practice just take it a few extra digits and you usually should be fine. You don't necessarily have to take every digit that's in the calculator if it gives you a long number. But if you carry it a few extra digits and stuff, you know, sometimes, you know, if you know like the top number should be 2 significant figures and you take it a few extra digits past that, you know, you'll be in good shape, you know. So personally, I would recommend not rounding to the very end, but you should definitely keep track of everything along the way. That way you can kind of clean it up at the end. And again, the real reason for that is, like I said, if you round a little bit here, then take that round number, then round again and again, you'll like move yourself far and far away from really the sort of correct answer. Other questions? Here, with just a straight division, so 3 on top, 3 on the bottom. And again, you can see the calculator in this case only gave us 1 significant figure. So we need to kind of correct that by adding some zeros there to get us to the correct number of significant figures. So, you know, your calculator doesn't really give it to you in the right number of significant figures. And again, if you're looking for your calculator, perhaps to give you the answer in scientific notation, unless you programmed it into scientific notation, it probably won't do that for you either in a lot of cases. So we do need to make sure that we just don't write everything that's on the calculator, because I've had people write numbers like, you know, and it just keeps kind of going and going and going and going. And there's like 9,000 digits for every calculation and stuff like that. So, you know, just keep that in mind that you do need to adjust some. All right, so give it a go, see what you come up with. Let's do the answer here to the correct number of sig figs. Okay, if we punch this into our calculator, and clearly just a reminder, a couple of things. If you have multiple numbers on top, you can multiply as many numbers as you like on top and then hit equals. If you have multiple numbers on the bottom, you should divide by the first number, hit equals, divide by the next number, and hit equals, and so forth. But if you do all the math there on the calculator, my calculator spit out 8.52, I hope, yes. All right, so let's talk about sig figs and where we should end up. Again, this top part here is what we probably would do first. So technically speaking, when we get the answer for the top part and we're multiplying, how many significant figures should it have? It should have 3 significant figures. That's because top number here has 3 sig figs. The one we multiplied the top number thereby has 4 sig figs. That means that the top number there should have 3 significant figures when we get it. The last math that we did was technically take that top number and then divide it by the bottom number, which is also looking at significant figures. Top number we established has 3 significant figures. Bottom number has 2 significant figures, which means my answer should have 2, which takes me to here, which means really this should be 8.5. Yeah. Any questions on that there? So again, I personally just punched everything in and then went back and looked at what I was doing and to figure out what my final answer should have in terms of significant figures. And obviously units would be good, which would be centimeters. Any questions on that one? All right. Now we talked about the adding and subtracting. Again, it is still the least, but it is decimal places we're looking at. So again, here, this first number has 3 decimal places, 2 decimal places, and 1. So on our calculator, it spits out this number here with multiple decimal places. Looking at the numbers we added, we would want to go to the least number of decimal places, which would be the first one there. And again, this guy here should be the correct answer, which is 66.1. It has one decimal place, but how many significant figures? And again, that's important in case you were to take that number and multiply it or divide it by another number. It would obviously be 3 sig figs in the next part of the calculation. Same thing with our subtraction. Again, least number of decimal places. And again, we end up here in this example here at 62.1. All right, you do this one here, add the following and give it to the right number of places. Okay, so in my calculator, I see it displaying 104.409, and these would be milligrams. In this case, I should take it to, yeah, we should go to here again, looking at decimal places 3 and 1. We would take it here. Obviously, this is a 0, so we could just drop the rest of the numbers. Gives us a 104.4 milligrams. Has one decimal place and how many significant figures? It does have 4 significant figures in that number. Question on that calculation there. And it agrees with me, so that's good. All right, any questions on sig figs, calculations with sig figs, rounding, anything like that? Okay, we're gonna, I think, move into kind of moving towards talking about conversions and dimensional analysis and, you know, these type of problems. We're gonna talk about prefixes and equalities. An equality, as I think we talked about last time, you know, it really is two things that basically represent the same amount of something, but they're on different units. So same thing here, you know, if we say, hey, we have 1 kilometer is 1,000 meters, they represent the same unit of length. They're just on different units. And as we'll talk about later on in this chapter as well, from any equality, you could kind of write 2 conversion factors. You could say something like 1 kilometer over 1,000 meters, or you can make it like a fraction of 1,000 meters over 1 kilometer. So we could use these, as we'll talk about, for conversions, and they do represent really the same amount of everything. These are what are considered exact numbers. Definitely these 2 that are shown here on the screen, as they are both metric to metric sort of conversions. Now, in the metric system, sometimes we get really big numbers, really small numbers. So we oftentimes will use prefixes to help us sort of manage those numbers. Like kilo is the prefix here. Kilo basically means 1,000. Milli there, it's basically 10 to the minus 3, or 0.001 is what it represents. So we have prefixes to make kind of numbers bigger for bigger numbers and ones that are smaller. Here, these are all kilo. And you'll sometimes see a table, and I think we'll see it in just a second, but you'll sometimes look at a table and you'll see the prefix, for example, and it'll say kilo is 10 to the 3, right? And sometimes people, when they look at this sort of prefix table, not really sure how to use it properly. And it's a very common mistake that people always sort of reverse the meaning of it. First off, when we see 10 to the 3, what that really is 1 times 10 to the 3, scientific notation is basically what that is. Now, what that means is when you take that like 10 to the 3, that is how much there is in the base unit to one of the prefix units. So what that means is you would say in one, say, kilometer, there is 10 to the 3 meters. And it's very common, people will kind of reverse that a lot and go, hey, there's 10 to the 3 kilometers and 1 meter, and that is incorrect. So when you see this table, I think we'll see it here in just a second, and you see it like, hey, milli is 10 to the minus 3. That is how much there is in the base unit to one of the prefix units. So what do I mean by base unit? I mean, like, for example, when we look at kilometers and meters, meters is the base unit, right? It's basically on both of it. This is like the prefix unit, if you will. It works for any unit. If I have 1 kiloliter, it's 1,000 liters, liters being the base unit on both. Again, by the way, 10 to the 3 is 1,000, right? If you do 1 times 10 to the 3 is 1,000. So that's where that number comes from. These are all 10 to the 3, basically. 1 kilogram, gram being the base unit. So again, there's 1,000 grams in a kilogram. So it's very, very common when people kind of use prefixes and calculations, they always sort of go, oh, that's like how much the prefix is to like one of the base, and it's actually opposite of that. Question on that there. And there is sort of part of that table, or and what we see. So for example, mega is 10 to the 6th. And what that would mean is in 1, say, megaliter, there would be 10 to the 6 liters. So in one of the prefix units, there is this much in the base unit. And it's really important to keep that straight. It's a very common error that a lot of people make when they see a table like this and they go, oh, kilo is 10 to the 3. They always sort of want to do it backwards. And as you can see here, it is 10 to the 3 meters and 1 kilometer as well. So truthfully, we don't really come across tera, giga, or mega all that much in this particular class, but definitely kilo we come across a lot, which is 10 to the 3. I think on the next page there's more of these, I would hope. Yeah, there it is. So centi we do come across, right, which is 10 to the minus 2. So how many meters would there be in 1 centimeter? So in 1 centimeter, there should be 10 to the minus 2 meters. Yeah. So again, that's how we pull those numbers off of this table. Milli we use a lot. Yeah, which is 10 to the minus 3. In 1 milliliter, there would be 10 to the minus 3 liters. So again, if you needed to put it into your calculator, you could put it in scientific notation as 1 times 10 to the minus 3. If you have like the E button or EXP button, you might just be able to, depending on your calculator, just put the exponent button and minus 3 and not have to put the 1 as well. So centi, I would say we come across a lot. Milli as well. Micro chemistry we do, and nano we do come across a lot. And again, for example, if you had 1 nanometer, that is the same as 10 to the minus 9 meters. So one of the prefix unit, one of the to the base unit is what it means. Questions on there? And by the way, again, it doesn't matter the unit you're using. By the way, if I had 1 centiliter, how many liters would that be? It'd be the same as this guy. It would be 10 to the minus 2 liters. If I had 1 centigram, how many grams would that be? 10 to the minus 2 grams, right? So the unit doesn't matter. The prefix is the same no matter what unit you're doing. But again, it is just one of the prefix units to whatever you see on this table, sort of in this column. Yeah. Any questions on that there? Okay, so that is a very, very common mistake. People kind of flopping those numbers around when they use those. All right. All right. So take a second here and see what you come up with. So the first one there is 1,000 meters is 1 kilometer. Remember, kilo there is, as we saw in that chart, 10 to the 3, which is 1,000. So 1 kilometer would be 1,000 meters. 1 times 10 to the minus 6. Really, if you're not sure, you would want to look on that table for 10 to the minus 6. And if you do, you would see it is micro. And that would give us 1 microgram. They write mcg. Sometimes you'll see microgram written like this, kind of like almost like a U type of thing is sometimes how a microgram is written. And lastly here, 0.1 liters is blank liters, and 0.1 is deci, and that would be 1 deciliter in that particular case. Obviously, you should be familiar with the prefixes, some of the ones that we use a lot, like I said, centi, kilo, milli, we use a lot. It probably would be provided for you in the form of like 10 to the 3, 10 to the minus 3. Again, you need to be able to sort of use that correctly and not backwards. So make sure you know how to kind of use it off that table. Any questions on that there on prefixes? Okay. All right, so let's talk a little bit about some equalities for lengths. And again, some of these we do come across a lot. 1 meter is 100 centimeters. We do see a lot. 1 centimeter is 10 millimeters, right? So I think we talked about the ruler the other day, right? Again, the big numbers on top are inches. Kind of the bigger numbers on the bottom are centimeters, and the smaller numbers are millimeters, right? So there's 10 little dashes there on the bottom of the ruler, gives you 10 millimeters is 1 centimeter. A little bit about some volumes. The volumes, I would say we definitely come across this guy a lot. 1 liter is 1,000 milliliters. It's a very common conversion that we use a lot here. I think we might have also talked about it earlier, but just a reminder that we can't get a volume by taking something like the length cubed. If you take something like the length times the width times the height of something like a cube, for example, those are all really length measurements. And if you did them all in like centimeters, you would have centimeters times centimeters times centimeters. And that is what is referred to as a cubic centimeter. And that is a volume. Yeah. So typically, if you take some type of length measurement and you cube it, it becomes a volume. A cubic centimeter is the same as a milliliter. It's a 1-to-1 conversion between them. And so we do see cubic centimeters a lot, especially when dealing with things like density. You see it a lot. And again, that is a volume when you do see something that's a cubic centimeter. Each of these individual measurements here, these are all length measurements, but when you multiply them together, it becomes a volume measurement. Any questions on that there? By the way, in medicine, they also call a cubic centimeter 1 cc for a cubic centimeter, right? Like give that guy 5 cc's of something before they die, right? And that's basically 5 milliliters and stuff like that. So here again is, as I just mentioned, our cubic centimeter are a cc. And again, a lot of times in medicine, they use cc. For solids, a lot of times, we measure the volume of the solid by, taking some measurements, length measurements. And then clearly, we talked about when we were talking about taking measurements, just a liquid in general, remember that whenever you're taking a measurement of a liquid, you always want to look for that curvature of the liquid there, which is the meniscus. And we read it from where? Yeah, we read it from the bottom of the meniscus, right? And again, as we talked about, really, even though it's sort of crawling up the sides of the glass, the real true volume, if it didn't have that attractive force, is kind of right there at the bottom. And that is why we kind of look for the meniscus and read from the bottom meniscus. Sometimes it's easier to see. Sometimes it's really hard to see the meniscus. If you have something that has a really big sort of opening, if you will, like a really big beaker or something like that, the meniscus gets kind of spread out and stuff like that. It makes it kind of hard to see it. But I know, I think you're doing measurements this week, right? So, you know, you want to try to make sure you kind of look for that curvature of the liquid. And there, as I mentioned before, very common in sort of medicine, syringes and stuff like that are in cc's a lot. And again, a cubic centimeter, cc, or milliliter, really all the same in the sense. They're basically all one-to-one conversions between them. Again, like I said, a lot of times solid things, like for example, something like density will be given the volume in cubic centimeters. Clearly, if you just read a volume off of a graduated cylinder or some type of piece of equipment, it would be in milliliters. And then obviously something like this is most likely going to be in cubic centimeters. Now, mass as well, a couple of very common equalities that we do come across. A kilogram is 1,000 grams. That is definitely something that we see a lot. A gram is 1,000 milligrams. So that also does come around a lot. So those two as well. You know, there is a difference in terms of mass and weight. And again, I think we might have talked about it earlier, but again, you know, the difference between mass and weight. Weight does take into account the force of gravity, and mass does not. So it's sort of independent of gravity. So typically when we do things like obviously weighing out something, we do typically refer to it as the mass of the object rather than the weight of the object. And you should do that as well. All right, let's take a look. So take a second here to just to finish up for today. For each of these, which one is the larger unit? So again, to the end here, millimeter, centimeter. There, sounds good. Kilogram, centigram. Deciliter, microliter. Deciliter. Micro is super small. Yeah, it's like really small. That is, I think that's also micrograms, I think is with that symbol. I'm not sure why they used it there or not there. Microgram versus milligram, probably should be milligram in that case. All right, any questions? Then that they use the milligram symbol there, but not here. I like it. All right. Any questions on anything we talked about here today? So we'll wrap it up there for today.